Hey everyone, today we're going to talk about how to determine the concavity of a function. This is Nicholas JMV. So before we begin, we got to look at a couple of things. So the objective for today is simple. If I give you a function, okay, you're going to be able to determine the interval where the function is concave up or concave down, okay? Concavity simply refers to the general shape of the graph, okay? So and what we mean by that is there's two things that are going to happen. Your function is either going to be concave up, it's like you can pour stuff into a cup, right? Or you're going to have concave down where stuff would just go off the cup, okay? It's important to realize that when you're concave up, your second derivative value is greater than 0. And if you're concave down, your second derivative value is less than 0. Okay, so that would be like a relative max, relative min kind of thing we're talking about here. So let's go ahead and look at a couple of examples I've got lined up for you today. Okay, so the first example, on what interval is the function f of x equals x cubed plus x concave down? So before you begin, you might think, okay, concave down. Well, that means my second derivative has got to be less than 0. Okay, so concave down, when we're talking about f double prime of x, is going to be less than 0. Okay, so that's the idea. So concavity deals with the second derivative, so I have to find the second derivative of my function. So I'm actually just going to go ahead and write the function over for you. Okay, so x cubed plus x. So now this is a power rule, so I'm going to go ahead and find the first derivative. Okay, and then I'm going to go ahead and find the second derivative. Now, this isn't like the second derivative test or anything like that. I don't need to find the critical values of the original function. I'm looking for possible points of inflection here. So the idea here is I have 6x. Okay. Now, if I want the concavity, I got to look for possible points of inflection. So I'm actually going to set the second derivative equal to 0. Okay. And the only time that this is possible is when x is 0. Now, here's the important part. We're going to do what they call a sign line or a sign analysis, okay? So I'm going to go ahead and draw a line, and I'm going to put on there my 0, which is 0, okay? And then I'm going to put 6x here up top, and then I'm going to put the value of the second derivative. Now, if I plug any number greater than 0 into the function, it's always going to be positive. 1, 2, 3, 4, so positive here. If I plug in anything less than 0 into 6x, it's going to be negative. So what we have found here is that before 0, the second derivative is negative, and to the right of 0, the second derivative is positive. We want to know where the concavity is down. That's where the second derivative is less than 0. So we can go ahead and write the interval from negative infinity to 0 is concave down. We know this, I'm going to abbreviate, because f double prime of at 0, f double prime, well, at f double prime of not 0, it's interval because f double prime of x is less than 0. There, that's the easiest, okay, to say. Sorry, I kind of botched that up a little bit. So the interval from negative infinity to 0 is concave down because the value is negative, okay? So that's our first example. Let's go ahead and do one more with a little bit different function. Okay, now we want to determine where the function is concave up. And now we're looking at the natural log of x squared plus 1. So f of x is equal to ln of x squared plus 1. Now I'm going to go ahead and find the first derivative, okay, which is the derivative of the derivative of this over x squared plus 1. Now, unfortunately, it's a little bit more challenging to find the second derivative. We got to use a quotient rule. So I go ahead and say bottom times the derivative of the top minus top times the derivative of the bottom, which is 2x, over bottom squared. Okay, so there's the second derivative. Now I got to clean this up a little bit. So the top, I'm going to clean up the top. We have 2x squared plus 2 minus 4x squared, all over x squared plus 1. Whoops. squared. Okay, now I get negative 2x squared plus 2 all over x squared plus 1 squared. Now, here's the thing. I actually, when we talk, if you've done this, we've done this a little bit, we're talking about concavity, talking about points of inflection or possible points of inflection. I actually have to set my fraction equal to 0. Now, the beautiful thing is the denominator here, okay, is never going to be 0. Okay, because it's x squared plus 1, it's shifted up, so it doesn't cross the x-axis, okay? The only way to make a fraction 0 is by making the numerator 0. So that's what we're going to do. So we actually just have to set our numerator equal to 0 here to find the possible points of inflection. So we're going to have negative 2x squared plus 2, and that's going to be equal to 0. Okay, I could subtract 2 from both sides. Okay, I divide by 2, so I get 1 equals x squared. So x is going to equal plus or minus 1. Okay, well, that's nice. So again, now we do our sign analysis. Okay, we have to figure out where our function is going to be concave up. So we have negative 1 and 1. And I go ahead and put negative 2x squared plus 2 up top. Okay, and then I put the denominator x squared plus 1 squared and f double prime of x. I have to put all those because we're dividing here. So now let's look at picking some values. If I pick anything greater than 1, this is going to be negative. Okay, anything, this is always positive. So here, here, and here is always positive. A negative divided by a positive is a negative. Okay, now let's look here. If I pick a value between negative 1 and 1, like 0, if I plug 0 into the top function, I get something that's positive. Okay, and then if I pick a number less than negative 1, maybe negative 2, negative 3, negative 4, this is always going to be a negative plus 2, so this is actually negative. When I divide a negative and a positive, I get negative. When I divide two positives, I get a positive. And here's the trick. Okay, so I plug in different values into my quotient here to figure out what the value is going to be. And we want to know where the concavity is positive. Well, that's going to be between negative 1 and 1. So we're concave up from negative 1 to 1 because f double prime of c is greater than 0. It's positive. Okay, so that's how you can find the concavity of a function using the second derivative in a sign analysis. If you have any questions or comments, you guys can share them below. We'll see you next time.